We spent the last chapters trying to identify the factors that would differentiate between mechanisms. The next chapters we will use to try to identify conditions that will give us the best yields of products that we want without side products. First, let's hone in on the conversion between alcohols and halides. We know that we can use a strong acid to convert the alcohol to a halide. The proton transfer makes a water-leaving group, and the halide can easily come in and displace the water. However, this reaction requires concentrated strong acids, which we will see can make all sorts of reactions happen, including SN1 and E1 reactions for secondary and tertiary carbons, which will give a mixture of products. Instead, we will generally react with PBr3 or PCl3, which will give good yields of enantiopure product. With PBr3 or PCl3, the reaction can occur without the presence of strong acid. The alcohol actually functions first as a nucleophile in an SN2 reaction, displacing a halogen from the phosphorus. The displaced halide then functions as a nucleophile that can replace the oxygen. Because the attacking halide is a weak base that reacts via SN2, there are no eliminations, and the reaction occurs to make only one isomer. Also, because we avoid forming a carbocation, we avoid possible hydride or cation shifts. This means the reaction is subject to all the limitations of any SN2 reaction. It only works on sp3 hybridized alcohol carbons, and it won't work with tertiary alcohols. The PBr3 reaction is common. We'll also see SOCl2 instead of PCl3, which reacts pretty similarly. Another class of substitutions uses amines as a nucleophile. The product is charged, but can be readily deprotonated by additional nucleophile and trapped as a neutrally charged amine. We generally talk about this reaction in the context of nitrogen as an alkylation, because we add an alkyl group to the nitrogen. But this reaction has one big problem. And that's that the primary amine that we form is actually a stronger nucleophile than ammonia, since the alkyls are slightly electron donating. So we can never stop at one alkylation, we always end up with a mixture of products. If you want a positively charged quaternary amine, which we call an ammonium, this reaction works fine. If we put in enough alkyl halide, eventually everything will react and the amine will become fully alkylated. This is really the only context where a direct alkylation of an amine is useful, because it's the only case where we get relatively pure product. Any way that we can form carbon-carbon bonds is rare and worth noting, because carbon is usually way less electronegative than other things and is positively charged as an electrophile. If we can make carbon into a nucleophile, that generally opens up a wide range of particularly interesting reactions. We've already seen some of these. We took sp hybridized carbons as alkynes or nitriles and used them as nucleophiles by deprotonating them. We can also use alpha carbons as nucleophiles. Remember from our common nomenclature that the position directly adjacent to a carbonyl is called the alpha carbon. Now, alpha carbons don't really react directly with an electrophile. But if we have base present, we can form a nucleophile that can react readily with an electrophile. Why is this difference? The alpha protons are actually reasonably acidic due to resonance stabilization. The negative charge is only partially on the carbon, which makes it more stable, but still quite reactive. Subsequent treatment with alkyl halide allows for alkylation at that alpha carbon. Many molecules have multiple alpha hydrogens that can be removed, which means multiple possible products if the reaction isn't symmetrical. Remember, the alpha hydrogen must be removed to form a charged product first. Common bases for this reaction include potassium tert butoxide and lithium diisopropyl amide. We can actually form two separate products depending on which base is used. This is because LDA is incredibly reactive. It is such a strong base that the reaction will be exergonic, and it will be under kinetic control. The tert butoxide is also strong, but will be endergonic or only weakly exergonic, and therefore reversible. There are two effects on the stability of the enolate, the conjugate base. In this case, the difference between the stability is mostly based on the substitution on the alkene, since the negative charge on the oxygen is the more significant resonance contributor. So the more substituted hydrogen is preferentially removed to form the more substituted alkene in the enolate, leading to a more substituted product. Changing to a different base doesn't change anything about which alkene is more stable. However, the more accessible hydrogen reacts faster, and since the reaction is irreversible, this determines the product that's formed. We can use other electrophiles with alpha carbons too. Bromine is a great example. Bromine doesn't have a dipole on its own, but it's relatively polarizable. This allows one of the bromines to act as an electrophile and the other to be a leaving group, and we can substitute a bromine onto the alpha carbon. The complete mechanism for this reaction is shown. The useful form of this reaction takes an aldehyde or a ketone and treats with a halogen in the presence of base, usually hydroxide. The result is an alpha carbon that has a hydrogen replaced by a halogen, and we can use chlorine, bromine, and iodine as those halogens. This type of halogenation works really well in basic conditions. However, an electronegative atom stabilizes the negative charge in the enolate. That makes each product more reactive than the reactants and ensures that the reaction will keep on happening until all the alpha hydrogens are replaced. In most cases, the amount of halogenation taking place under basic controls is undesired, but we can arrive at a similar reactivity without forming the enolate if we use acidic conditions. An acid is used to protonate the carbonyl oxygen, which in turn makes the alpha carbon much more acidic and forces the equilibrium of the keto-enol tautomerization to the enol. This doesn't carry the negative charge that the enolate has, and so it is less reactive, but through a similar mechanism. Because the charge is opposite in the rate-limiting step, the reaction will stop after a single halogenation. Carboxylic acids can also form nucleophiles, albeit very weak ones. A specialized application is the formation of methyl esters by treatment with diazomethane, that's CH2N2. Diazomethane is a neutrally charged molecule, but carries some extra electron density that can easily deprotonate the acid. The resulting molecule is really unstable and quickly reacts irreversibly as an electrophile with nitrogen gas as a leaving group. Because the nitrogen is a gas, the reaction is very irreversible. This is our first set of specific applications of SN2 reactions, but don't worry, we've got more in the next section.